So let us introduce the basic arithmetic on this p-adic number. So I chose the two examples of p-adic integers, and this has this following pattern: 1 and 2 as the first two digits, and 1 and 2 and 2 repeated 2 times, and 1 and 2 repeated 3 times, and 3 is here at the first digit, and 4 and 3 repeated 2 times, and 4 repeated 1 time, 3 repeated 3 times, 4 repeated 1 time. It's a similar pattern, so at least you understand this dot 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 clearly. So if you have these two p-adic numbers, integers, and we're going to go through and how we're going to add these two numbers. It's very simple. It's of course based on the arithmetic in a modulo p to the k, which is basically the arithmetic on the integers. So we're going to add these two numbers, 1 and 3, and they're lined up like this. So it's 4. Because this addition does not exceed 4, which is largest number allowed in p-adic 5-adic. I forgot to mention in here, the p here is 5. So that's 4 is going to come down here. But if you look at the second column, second digit, 4 plus 2, it exceeds 4. So 4 plus 2, every copy of 5 in the coefficient is carried over to the next digit. So here 5 goes into 6, as 1 is a remainder. So you're going to have 1p, and there will be a carryover to the next digit. So this is 1 plus 3, but 1 is carried over from earlier digit. So it's going to be 1 plus 3, but with a 0, because the coefficient becomes 5. That's carried over to the next one. Now this is already 5, but it's 1 is carried over here, so we're going to have 1 down there. So that's why we have this coefficient of 1, 3, and 2 plus 4, it's a 6, so it's 1 is a remainder, and it's carried over next to the part. So that's 2 and 3, 0, carried over to the next digit, so it's 5 and 1, so that's 6, so 1 remains here, carried over to the next part. It's already 6, but 1 coming from the earlier place, so it is 2, so that's a 4, but carried over here, so it's a 0, carried over to the next part. It's a 5, but we have 1 from earlier, so it's 1. So 5, so 1 was carried over as 1, and here's a 6, but 1's carried over, here's 2, because it's all together, it's 7. So 2, and keep on going like this. Although we didn't finish this computing the each digits, it's clear that if you do that, if we choose an arbitrary place like p to the 100th, like here, then we can calculate that by doing this one. And once you calculate this 4, it's not going to change at all. It stabilizes like this. As we add, it always carried over to the right. So there's none of these numbers on here that we have calculated already is going to change because of the addition in the next digit, which is the case if you look at the usual decimal expansion in the real line. As you add these two numbers, if it is a 10 to the negative 7 and 10 to the negative 7, it's carried over to the next digit, so it possibly changes something that you have calculated already. But here the p-adic integer is a lot simple. Now let's consider the subtraction. In this place here already, we're subtracting 1 from 3. It's because we can't do that. We're not going to have a number in between 0 and 4. We have to borrow from the next digit, and this is already small, that you are borrowing from another one, and so on. So we're doing something to the left, so it could be confusing and not very convincing. So what we're going to do is the following. So we're wanting to consider this x minus y, but algebraically you can rewrite it x plus negative y. So if you explain the meaning of the negative y, then we can use this negative y and add these two p-adic numbers rather than subtracting it. So here's how you compute the negative y. If you add these two numbers, y and negative y, is supposed to be 0. So if you start from 3, 4, 3, 3, 4, 3, 3, 3, 4, and that's the copy of this y, what you have to do figure out is to figure out each digit such that each of the digit becomes 5. So if you start with 3, if you put 2 there, that becomes 5. So it carries over to the next digit. Now it's already 4, so 1 carried over, so it's already 5, so I don't have to add anything. So this is going to be 5p, but p is 5, so that's the same as p squared in here. So p squared carried over to the next one, then it's going to be 4p squared. So if I have one more p squared, that becomes 5p squared. 5p squared is the same as p cubed, so carried over to the next digit, so 4. So I have another copy, that makes 5. Already 4, carried over here, so it's already 5. So this is 3, carried over, so 4, so you get p to the 5th. Except the first digit, pretty much the rule is that 4 had 0, 3 has 1, and if there's ever a 2 appeared there, that's going to be 2. So whatever that makes 4 in each digit, that's the rule except the very first digit. And that's going to be negative y, because if you do that, each of the coefficient of a p to the power clear to 0. So as you continue calculate, it's going to be always a 0 everywhere. So that satisfies this condition that all the coefficient here is 0. So negative y has this p-adic integer version. So again, instead of subtracting these two numbers, we're going to add these two numbers, and that'll be this same as x minus y. So if you add this one is 3, and if you add this one is 2, and so on. There's no coefficient that exceeds 4, so it's simply adding all those coefficients. So that's how you subtract two numbers in the p-adic integers. Now we have defined an addition and subtraction in this p-adic integers, and using that we can introduce the modular arithmetic on the p-adic integer. Remember, the modular arithmetic introduced at the beginning is for the integers, not for the p-adic integers. So if you have two integers, p-adic integers, alpha and beta in ZP, and alpha minus beta, if you do the subtraction that was just introduced, if they start from p to the nth level, so a p0, pn, a1, p to the n plus 1, there's a reason that coefficients are indexed in this way. But if the difference starts from nth level, and we're going to write alpha minus beta is congruent to 0 mod p to the n, and where alpha and beta is just p-adic integers. And also write alpha is congruent to beta mod p to the n. And of course, this extends, this is a generalization of the definition of the integers. So if you happen to have alpha and beta as rational integers, and this definition coincides with the definition was introduced for integers. For p-adic integers, what this really means is that if you look at the p-adic expansion of alpha and beta, it means their coefficient up to p to the n minus 1. It's going to be exactly the same, and starting from p to the n, we have a different, might possibly have a different coefficient. So if you subtract those two numbers, and everything will cancel because they're exactly the same coefficients, and it starts from p to the n, as I explained earlier. And since everywhere it has a copy of a p to the n, you can kind of factor out naturally, and introducing a natural multiplication of a power of p to this p-adic integers that is written in that form. That's why it's indexed in this way. So that's the meaning of two numbers congruent to each other in p-adic integers. Another notion I'd like to introduce in here is that this p-adic integer being congruent to 0 mod p to the n for all n means alpha is 0. Because as you increase this level n, that it's beginning to reveal and more coefficients, being 0 means all the coefficient, no matter what level you look at, is all 0. That's the definition of a 0 in the p-adic integers. So now let's consider multiplication of two p-adic integers. And all the addition and all the four basic arithmetic is well defined. What I'm trying to go through in this video is just introduce the method of actually doing that calculation, not necessarily justifying all these things are correctly defined. So here our goal is that we have this possibly infinite sequence, potentially infinite sequence of 0 to 4, for example, if it is a p-adic, and here another number. And how are we going to multiply this one? The result should be another p-adic integers, like this. So we have to be able to specify, okay, if I want to calculate the C10, and what is the algorithm that allows us to calculate? Just like we did for addition and subtraction, there is a way to calculate this one digit at a time by expanding and looking at the arithmetic. I did that, and it's one way, but it is not that efficient way of doing that business. It's not that neat as adding and subtracting those two p-adic numbers. So I decided to just the way I implemented a computer program to carry out this calculation, which is, I think, is more efficient algorithm. Idea is the following. First, we look at this infinite sequence x and infinite sequence y, and we decide to truncate at nth level. So xn has the same coefficient all the way up to p to the n. So we can use this modular arithmetic congruence relation, p to the n plus 1, so up to nth power, their coefficients are exactly the same. Instead of dealing with x and y that has infinite sequence, if you deal with xn and yn, which is finite sequence, the arithmetic that you do on here is correct and up to this level, and that's the idea. So before we calculate, we have to make a decision. Okay, if there's infinite sequence and infinite sequence, of course we can't do that infinite sequence, so we have to have a target. Okay, let's get the C0 all the way up to C100. Let's get that number correct. Then we can look at x100, deal with that number, and y100, that finite sequence. So what I'm writing it here is, although it's a part of these p-adic integers, once you truncate it like this, this is actually the rational integers. It doesn't go to infinity, so you can just multiply this out, turn it into a usual integer decimal notation, and you can do that in here too. Once you have that number and convert it into decimal expansion for the computer, and modular arithmetic is the same as integers, you can multiply side by side. So xn times yn, the number you get in here, will have at least the same p-adic coefficient up to the p to the n in the right hand side, which is what we're about to define. Not about to define, we're just assume it's defined and try to calculate the coefficient up to n. So if you look at these two numbers, and although it has p to the n, if you multiply, you can see we have at least the p to the 2n kicks in, but that does mean it's stopped at the p to the 2n. If you multiply a0, b0, and all this cross possible multiplication, those products that usually don't stay in between 0 and 4, it exceeds 4 usually, so you have to clear out into a new the correct p-adic coefficients. So that's why the xn times yn look like this. You can go all the way up to whatever the coefficient up to p to the nth power, and there will be more and more coefficients. So we don't exactly know what this m is, but it's going to continue like this. But what this modular arithmetic guarantees here is up to the nth power, the coefficient is the same coefficient as x times y as a p-adic numbers. So what I did in the computer program, when I implement this one, I turn this xn to usual integer and turn the yn to usual integers. The computer recognizes they know how to multiply these two numbers as usual integers. Then just rewrite it as a base p expansion, and then just use up to nth power, because we know up to that is the correct coefficients. And that's how you practically multiply this infinite sequence of two numbers and get a correct coefficient for the product of these two p-adic numbers. Imagine the situation that you calculated the xn and yn, and then you wanted to actually compute the one mode, and you don't stop it here. For example, here n is 10 and n is 10, if you want to compute the C11, not C10, then you can repeat this computation again. And here's actually what happened if you compare that product, an xn, yn, with the higher level product, xn plus 1 and yn plus 1. And if we compare these two up to the p to the n, because we're truncating it at the p to the n plus 1, so this is only we're comparing up to the nth power, and they're exactly the same. So what we discovered here, C0 to the Cn, is the same as the same coefficient we discover in the next level. So if this is guaranteed, then pretty much that can be used as a definition of this multiplication process. So these being equal to each other up to this level is equivalent to the well-definedness of the multiplication of two p-adic numbers. Now let us introduce the division of the two p-adic numbers. I think this statement here is probably the simplest statement about the facts about the division of the two p-adic numbers. So this is a typical presentation. If y, that is going to be the denominator, so we're dividing x by y and see if the quotient is still in that p-adic integer. If the divisor starts with a non-zero coefficient in here, then it's guaranteed that it will be able to divide it here. That means there is a number in ZP which is a quotient. So if you multiply that quotient to the divisor, you get the dividend back. So that's the meaning of the division. So we're about to go through an algorithm that looks a lot like a long division algorithm. So let me explain what happened in the long division. So this is decimal expansion. This is usual real number. So it's 1/3, and we try to figure out what is the digits, decimal digit of 1/3. So to figure that out, we write it like this: C1 divided by 10, C2 10 squared, C3 10 cubed, and so on. To figure out the first digit, what we do is that we multiply this quotient by 3 and write the dividend on this side. And to turn the C1 to an integer, we multiply 10 both sides. Then this one becomes a 10. It's mainly because this one here is less than 3, and if it is greater than 3, we will throw in some integer multiple in between the parentheses and C1 divided by 10 there in that space to kind of reduce this one, but it's already small, so there's no integer that can go in there. So that's why we turned this number into something larger by multiplying 10. So 10, 10 is multiplied, so now C1 becomes an integer, and this one reduces the level. Now there is a number that you can put it in there, and an integer that kind of knocks down this 10 to make it as small as possible. So the choice of that number is of course 3. That's the largest positive number you can put it in there. So this 9, if you subtract it off, and you get 1. So this number is again smaller than 3. Then if you multiply 10 again, and you repeat this procedure over and over again, so by multiplying it 10, you repeat this 10, and C2 now becomes an integer without 10 in the denominator. Then it's pretty much in the same situation. The maximal multiple we have is 3. So we put this one into a long division algorithm as follows. Like this 1 there goes up there, and realize the 1 is smaller than 3, so we multiply 10, so that's why you put 0 on there, and figure out what is the maximum multiple that is get close to 10, but less than or equal to 10. Then it's 9 by 3 times 3, and you subtract it here, 10 minus 9, and you get new remainder again, so you multiply 10 and so on. So that's justification of the long division algorithm. So we're going to do similar thing to the p-adic division. So here's how it looks like. 1/3 in p-adic 5-adic numbers, that's what we are trying to calculate. So again, that number we try to figure out is going to be the quotient. So 3 times what number is going to be 1. That's the dividend. So we have to figure out this A0 and A1, A2 one at a time. the first one, the key thing here is that we're trying to make this one number as small as possible in the decimal expansion of the division. And here we have to match the congruence class of 1 in the right hand side, and that turns out to be the key. So this is in between 0 and 4. Think about which number, if you multiply 3 there, then it becomes the same congruent class as this. That one is congruent to 1 mod 5. And see what that does. If you look through 0 to 4, turns out 2 is the ones. If you multiply 3 times 2, you get 6 there. 6 is 1 mod 5. So if you subtract this number, 3 times 2, both sides, and because 1 and 6 is the same congruence classes, congruent to each other, what you end up at here is something divisible by 5. 1 minus 6, the 0 mod 5. That's why it's divisible by 5. Then after you get rid of this a0, what happened is that this part here is divisible by 5, because that's what we chose. Then everything here has a p in it. So you can kind of divide all the 1 copies of a p everywhere. So that if you divide it by 5, that becomes -1. If you divide everywhere here, that becomes another p-adic integer, kind of shifted and losing that a0. That's what happened here. From here, it's the same algorithm. You have to figure out between 0 and 4 in here, such that its congruence class is congruent to -1. So if you look through it, that turns out as a 3. That's a 9. That is congruent to -1, which is congruent to 4. So if you look at 4, it's easier to see 9 is congruent to 4 mod 5. Now this 9 is subtracted. Then of course is -10 is divisible by, of course, 5. So you knock down these p's everywhere. Then if you divide this one by 5, you get -2. So here's a2 with losing the 1 copy of 5 in here. And this -2, that's congruent to 3 mod p. So to match that, by choosing this appropriate, this is 1. 3 times 1 matches this congruence class on the right. And you subtract again, and so on. You keep doing that, you will figure out 1 digit at a time. And I'll put this one into an algorithm like this one, so that we can do this calculation efficiently, which is this one. So the 1 divided by 3, so I put 1 there, and the 3 is a divisor. The number you choose in here is between 0 and 4, thus that the 3 times 2 matches the congruence. That was 2. 3, 2 is 6. If you subtract 6 from 1, -5. And we don't deal with the -5. We divide this one by 5, excuse me. It's -1. Now you start all over again with this -1. So the congruence class that matches -1, it was 3. So it's 9 if you subtract -10. And you divide by 5, -2, and 3 matches it, -5. If you subtract it, and if you divide it by 5, you get -1. Remember, we just repeated -1. We start from -1, and the rest of the part is completely determined by this sort of remainder in this long division process. This 3 is determined by this -1. So if you start from -1, it's going to be, of course, 3 to match that congruence. So what happened in between in here, -1 and -1, will be repeated. So 2, 3, 1, 3, and 1, 3. This 1, 3 is 3, 1 repeating will be forever. So the 1/3 in a 5-adic integer is 2, 3, 1, 3, 1, 3, and that's the infinite expansion with this repeating block. These are another set of examples. So dividing 2 by 7 is very similar a calculation, so I will just leave it here for you to see and to check answers. But I'll say something about this part here, dividing 1 by 33. I chose this larger number to show you what happens. So these are again a multiple number in between 0 and 4 that matches the congruence class of whatever you have it at this corner of this algorithm. So for example, let me just choose a random one here. So we're looking at the -29. So I think that's 4 mod 5. Okay, and this is 3 mod 4 mod 5, so I was wrong. This was a 1 mod 4. This is 29 is a 4 mod 5, so negative is going to be 1 mod 5. So 6 is going to be 1 mod 5, and so that's why this has the same congruent to each other mod 5. So 3 times 2, 6. And that's all you have to match because our p is small enough, and that's all that matters. All right, that's how you compute all these numbers in here. But you notice that these remainder, after you factor cancel the one factor of 5 everywhere, you have these remainder, negative 13, negative 29, negative 19, negative 17, and negative 10. And it'll go on for up like this. For this 6 numbers, they're all less than 33, and that's what I'm about to explain. So all this number we have here is less in between 0 and negative 33. So inductively, I'm going to show that an plus 1 is also in between negative 33 and 0. What we do to get an plus 1 is that you subtract here. These are an. You subtract these number, which is multiple of 33. So an subtracted by negative 33k, and since an is in this range, I'm doing the same operation, subtracting negative 33k everywhere. And to get to the next number, you divide everything by 5. So I divided by 5, and I calculated the maximum of this number as it was k varies from 0 to 4, and I calculated the minimum of this number as k varies from 0 to 4. To get the maximum, you have to replace the minimum of k here because of a negative, so that replaces 0. To get the minimum of this one, you have to replace with the maximum, which is 4 here. Then that's going to be negative 33. So if an is in here, an plus 1 is again trapped in between in here. The reason I examine all these, this fact is that as we keep continuing doing this algorithm, we guarantee that the number you see here is always in between negative 33 and 0. What that means is that because there are finitely many integers in between negative 33 and 0, it's going to repeat eventually. Repeating means, for example, negative 29 may appear again. Maybe that's not the number, maybe something else will appear. Anything that is in between 0 and negative 33 will appear one more time. But in between that, it's going to repeat it again and again, just like we saw for the 1/3, because each of the next coefficient and all these numbers are completely determined by whatever the remainder you're looking at here. Therefore, we can conclude that this 1 divided by 33 is a periodic coefficients. So eventually it begins to repeat certain block ever and ever again. So I use a computer software to actually calculate these long division. The way I actually did it with the computer is just like the same way I did it with the multiplication. I didn't really go through that individual long division process I showed, and which is makes more sense when you do this by hand. But the computer you can do it better and faster, but should show the same result. So it turns out these second 10 digits are repeating over and over again. Okay, so this is a repeating block. In the next part, I'd like to argue that if you have n divided by m, no matter what those are, as long as they are rational integers, the usual integers, you will end up at periodic coefficient. That's what I want to explain. So we did understand this long division, the process, then that makes sense for whatever number we have it here, as long as there are 2 integers. So if one of the numbers are negative, you can put that negative to the dividend and keep your divisor always positive. So you may have a negative number here, you may have a large positive number, but I think it's easy to see that this long division process will eventually take this number down to some sort of negative number, because we keep subtracting from whatever the dividend you have it here. If it is already a negative number, then since we're subtracting positive number, you will end up at negative number. So I think it's sufficient to explain the periodic property starting from the negative numbers. So that's why I stated like this. N is going to be on negative rational integers, and this condition is not necessary. Please do not read this part. N is just any negative rational integers, not p-adic integers. So it's going to be written like this, and this part is also unnecessary. Sorry about this. So N is just the negative rational integers. And we have these remainders. I'm showing you this again. So that's your N. This is your first remainder after you knock down that 5, one copy of 5, and this is the second remainder, and that's the third remainder, R0, R1, R2. That's how it's labeled. That's what these remainders are. M is our divisor, and please excuse that notation. This I haven't introduced this notation, so suppose this is integer is not divisible by 5. That's equivalent to that. So here's a summary of what we do. So we start from n, and we subtract some multiple of m, and we divide it by p. That's what we do to get the first remainder. If you have a kth remainder, you subtract some multiple of m and divide it by p to get the next remainder. So that's how you calculate it. The starting point is this. We got to know something about this n. So n is trapped in between negative m times c. This is a one integer multiple of m, and this is the next level to the left. So there should be c that in between that n belongs to. So I'm going to abbreviate the c plus 1 with the c prime. So I'm going to do this one and subtract both sides, the multiple of m, and divide it by p. So let me explain this side, and I subtracted this a0m, and I factored out the negative and an m, so that's why you see this c plus a0 in here, and divided by p. On this side, this whole thing is called just a c prime, so the same thing I subtracted, but inside the parenthesis, just addition, and divided by p. And I replace this one with the maximum value, replace this one with the minimum value. The maximum comes from the minimum a0, so which is 0, so that's why you see this one, and replace a0 with the maximum, so that's how you make this one minimum. So this one becomes p, so that's just 1. So what happened is that it keeps the same form. If you start from n, the first remainder r0 is obtained by simply replacing this factor with the c over p, and this factor c prime with the c prime divided by p plus 1. So since these things are again in this form, negative m times some number, negative m times some number, if you do this process one more time, then it'll do the same action to this factor multiplied to m part. So namely, this is what happened to the right hand side, negative mc. This is supposed to be p. That one is divided by p. Negative mc prime is divided by p and added by 1. That's what happens to the multiplicative factor. So we're going to repeat this over and over and see what happened. So this was r0, it's in this shape. So right hand side is divided by p again. That's what happened to the right hand side. Left hand side, you divide all this thing by p, so we have p squared and p in there, and add 1. So that's going to be the range where r1 is going to be in. So you keep repeating and divided by p and add 1 and divided by p in here. You can easily see that this becomes some sort of geometric series, and this is simply just p to the n is going to appear in the denominator. So when this index here is 1, you go all the way up to the second power, so I think it's going to be like this, rk, then we're going to go all the way up to k plus first power in here. Just have to simply estimate this one and see what you get. Alright, right hand side, you can easily see that it becomes 0, and c is fixed and k is growing, so this is going to be 0 in here. And this is a geometric series. As you add more and more, we can estimate this one. It's funny that we have this last term as the c prime is multiplied. So if I multiply c prime everywhere, that's necessarily greater than or equal to, so that's going to be even smaller than this one. So that serves as a nice lower bound. So instead of 1, we have c prime and c prime and c prime everywhere. You factor that out, and then it becomes usual clean geometric series. And that has this formula, 1 divided by 1 minus the common ratio, which is 1 over p here. So this part here is the same as p divided by p minus 1, quite close to p. The good thing is that there's no more k here. Nothing is changing as k changes. So our k is trapped in between these two numbers. So that'll force the rk eventually repeat numbers, and rk plus 1 is completely determined by rk. So if rk repeated, whatever happened in between those two occurrences will repeat it over and over. So that proves p-adic expansion of n divided by m where there are rational integers, z. It's necessarily periodic and even in p-adic expansion. So I summarize it here. N and m are the usual integers, rational integers so-called. M is a positive, n can be negative. And m is a number that is not congruent to mod p. Then this n over m exists in p-adic integer, as the long division kind of indicated, and also these coefficient eventually repeat, and there is a repeating block. For the rational numbers, the converse is also true. If you're looking at the decimal expansion with a repeating block, that is a rational number. The algebraic trick that goes into that is exactly the same, so I'm going to explain it here. So having the fact that the p-adic coefficient repeats as a repeating block is the following. Up to a certain point, suppose there's no repeating block, there's no pattern. So we can convert up to that into an integer, right? For example, it starts from p to the s here, so up to the p to the s minus 1, you can convert that into an integer. Then starting from the s level, and we have these coefficient repeating all the way up to bm, then this coefficient to begin to repeat again, b0, bm, next part b0, bm, it keeps repeating. So I looked at these powers carefully. It starts from s, it's supposed to end at s plus m, this one is s plus m plus 1, and so on. So for each repeating block, I factor out the maximal power p to the s. Second one here, of course, it starts from here, so that's what's going to be factored out. And next one, so you go from here is m plus 1, so for the next block you have to go another m plus 1, so it's going to be 2 times m plus 1 added to s there. So after you factor out, what's left here is a b0 to bm as an integer, and after you factor out, it's going to be exactly the same. You see this whole thing is factored out, a b0, b1 times p to the first, and so on. So this m here will be repeating as a multiplicative factor, but this is not in between 0, 4, anything. It's some number multiplied to p to the s. So m's are all common, so you can factor out those m and all the common smallest power of p to the s in here. So p to the s, m is factored out 1. P to the s and m factored out leaves p to the m plus 1, and p to the s, m factored out leaves 2 times m plus 1. So if you look at this part, this is again the geometric series, but this geometric series is happening in the p-adic integers, right? That rk that we were looking at before is really the global, the rational integers, so the calculation is really happening in the real lines, but this is not happening in real lines. So the concluding this one is the p-adic integer formula holds. I mean, the formula for the geometric series still holds for this type of series. Is something they have to think about. One easy way to do that is you go up to a certain point. Let's say instead of 2 here, let's go all the way up to capital N. And that's a finite sequence, so you can use the formula for the finite geometric series, and you will have some factors up there. And if you reduce that to modulo p to the whatever the high power, you will see that they're congruent to each other, and from that you can conclude even in the p-adic numbers, the power series converges to that. Simple way to demonstrate the difference between the geometric series and the real line in the p-adic numbers is that if you happen to be looking at geometric series like this, where the common ratio is not divisible by p like this, something else, then you may have a different result. But because the common ratio is a p, it involves a p, the way the geometric series works is exactly the same as the way it works for the real line. So the key thing to conclude from here to there is a common ratio here is divisible by p, and that's the key statement to go freely use that formula for the geometric series. Now once you have that, what we have here is n, the rational integer, p to the s times m, rational integer, and that is a rational number. So everything is a rational number. So whenever it has a repeating block, you can turn that into a rational number like this. So let me summarize some of the facts. In Z, the integer, even in the negative integer, we're able to identify in the p-adic integer. And if you have a quotient of two numbers, as long as m down there is not divisible by p, then in the long division process, you can always find the coefficient that matches the congruent class down there. That's where this condition is used. And from the long division process, we know it's sitting inside the p-adic integers. When you convert those, if it is integers, it'll sometimes just terminate to somewhere. If it is negative, you expect that there will be some p minus 1 repeated. In 5-adic, when p is 5, we will see 4, 4, 4 repeating at the end. So if this happens, you can recognize that, okay, that must be a rational integer. Or in that expansion of the p-adic numbers, if you realize that there's a block that's repeating forever, then you know that's actually the rational numbers. So you can recognize rational numbers and integers by looking at p-adic expansions. Remember, that was one of the goals in the modular arithmetic. As you look at higher and higher levels of the modular, and maybe we'll pick up rational solution and integer solution. Here's one way to recognize it. Of course, you can do that using the real numbers expansion at the same phenomenon, but it is arithmetically more plausible and more accessible. That's the way to phrase it. In this video, we're going to summarize some of the basic facts about algebra of this p-adic integers. So all the p-adic numbers are represented by these infinite sum, and we've seen that, and these numbers as reciprocal is divisible whenever the first coefficient is non-zero. So it will have its own reciprocal within that one, within the p-adic integers. So if it starts with a non-zero, there will be a number in the p-adic numbers such that x times y equals 1. So for example, like this, if it's p is 5 and 2 is not equal to 0, therefore there will be a number in the p-adic integers such that multiplied to this number becomes 1. That kind of number is called a unit, and a collection of units is denoted by zp star. This itself forms a multiplicative group. That's the term used in algebra. And you can see there are a lot of units there. If you think about the 4 possibilities for a 5-adic number, so 1, 2, 3, 4, that's what is allowed in the first spot, but there is no condition whatsoever for the rest of the part. So the cardinality of a collection of numbers that starts with a non-zero coefficient is equal to the cardinality of the real number. So there are infinitely many, actually uncountably many units in the p-adic integers. So that's one difference. It had some sort of integer structure, but it has lots of units like this. The second factor listed in here is the prime numbers. And this, there are a lot of units, so they're not considered even for the prime numbers, but the numbers like p, it does not have multiplicative inverse, so that turns out it's actually a prime. And there's no other prime, essentially. If there is a prime, like an irreducible, then that irreducible or prime must be unit multiple of the prime p. So this is called an associate. So all the primes associate to prime p. So essentially there's only one prime. And like our rational integers, this has unique factorization property. Any number you choose in the p-adic numbers in here, it factored uniquely, but there's only one irreducible, one prime, so that's mainly what that's about. The power of the prime here times a unit. This is always written in this way, and n is unique. So that's an integer structure. This has unique factorization property. Then you can consider field of fractions, field of quotients of these integers, and that'll make us go from integer to the rational numbers. Since there are a lot of units, you don't have to consider the inverses of those units. You just have to take care of that p part. The p is a number, the prime, that does not have multiplicative inverse. So to throw in all the multiplicative inverses coming from p is simply allowing in our expansion, not starting from p to the 0, we're starting from p to the any integers. For example, these look like another power expansion of p, but it starts from p to the -2, p to the -1. In the function, we've seen something like this called a Laurent series in the functional theory. But if you start from p to the any power and getting higher, then you can reorganize this number like this, p to the -2 and p-adic integers. So it looks like x is p to the -2 times p-adic integer. And you can see u is already a unit because it starts from non-zero, and p to the -2 has p squared, it's multiplicative inverse. So if this were an integer, now we have this as a multiplicative inverse. So you can easily see that if you write numbers in this way, all the numbers in here has multiplicative inverse as long as it's non-zero. So this turns to a field, and the field of fraction of p-adic integer look like this.